Hello and welcome to your favorite Shridevi classes YouTube channel where we inculcate interest and confidence in engineering education. Today in our playlist Induction Motors we will discuss speed control of three-phase induction motor and we will study the stator side control in which the simple and economic variable voltage supply to stator can make variation in speed torque characteristic to get variation in speeds. Similarly, special designed stator winding could have a provision to change number of poles, and by that we can change rotating speed of induction motor, and we can also use modern power electronic variable frequency drive, and when we supply variable frequency electric voltage to stator of induction motor, we could get continuous varying, smooth, controlled and very effective and efficient speed control of induction motor. Let's understand stator side speed control of induction motor in this video. Electric motor shown in this blue ellipse is three-phase squirrel cage induction motor, which is most popular electric prime mover used by our world due to its economic, rugged and almost maintenance-free basic design and operation. More than 90% motor used in industries are of such three-phase squirrel cage induction motor. At no load conditions, the rotor of induction motor rotates almost at a speed of rotating magnetic field, synchronous speed, and the speed difference of rotating magnetic field and motor rotor is just 0.5% of synchronous speed, and at full load conditions, this speed difference may become 5% or 6%. So we can say motor in its entire operation zone from no load to full load have a very small speed regulation, that's just 5-6% of synchronous speed, and we can say induction motor is almost a constant speed motor. That's why majority of industrial, agriculture and other sector activities use induction motor for constant speed operations. But in some industrial applications we may require speed variation or speed control of such motors, and for that we have to use special measures to obtain speed control in such three-phase induction motors. Let's understand theory of speed control in an induction motor. In an induction motor, when three-phase space displace winding is excited by three-phase time displace excitation, then between stator and rotor in the air gap, a rotating magnetic field of constant magnitude and constant rotating speed get produced. Now the speed of rotation of that rotating magnetic field is called synchronous speed, ns in RPM, and that speed depends upon the frequency of three-phase supply given to stator, F, and the number of pole for which stator and rotor are designed, that is P. So for F frequency and P number of pole, the rotating magnetic field speed called as synchronous speed in RPM is given by 120 F over P. Now due to electromagnetic induction and speed difference between rotating rotor and rotating magnetic field, current are induced in rotor, and those induced current interact with rotating magnetic field and rotor start rotation by electromagnetic torque developed in rotor in the direction of synchronous speed with a certain amount of speed difference, and that speed difference is represented by slip, and for S amount of slip, then rotor speed NR in RPM is given as NS 1 minus S. The rotor speed in RPM is given by this relation represented in this blue frame clearly indicate that we can change rotating speed of induction motor rotor by either changing rotating speed of rotating magnetic field NS by change of supply frequency or change of number of pole in rotor winding, or we can also get speed variation in induction motor by change of slip. Now the slip depends upon equilibrium of motoring torque and load torque as per torque slip characteristic, but by certain means we can modify or change torque slip characteristic of induction motor, and by that change for the same amount of load we can get different amount of slip and different amount of rotating speed. So speed of induction motor can be changed by either by changing frequency of supply to stator or number of pole in stator winding, or by the change of operating slip in induction motor. In this blue ellipse, the rotating speed of induction motor rotor in RPM is related to synchronous speed of rotating magnetic field and operating slip of motor by this yellow highlighted relationship, and this relation clearly indicate that we can control speed of induction motor by either control of synchronous speed of rotating magnetic field, and that can be controlled by change of supply frequency given to stator winding, or we can have special designed stator of induction motor where we can change number of pole in stator winding, and we can also change torque slip characteristic of induction motor by several means, and by that variation in torque slip characteristic, for the same amount of load torque we would have a variation in operating slip, and variation of slip may result in variation in operating speed. So speed of induction motor can be changed by 5 popular methods: the change of supply frequency to stator, or change of number of pole in stator can change synchronous speed of rotating magnetic field, and by that we can control speed of induction motor. And we can also change torque slip characteristic of induction motor, and by the change of slip operating speed of induction motor can be controlled. And this change of slip or slip torque characteristic can be achieved by change of just stator applied voltage without change of frequency by simple convenient tools, that is called stator voltage control. And if our motor is slip ring induction motor, then we can also change slip torque characteristic by insertion of extra resistance in rotor circuit across slip rings in a phase wound rotor, and the same type of characteristic can be achieved by injection of slip frequency EMF in rotor circuit. Now a special method can also be used in two slip rings motor when they are cascade operated. Then the cascade operation of two slip rings can also achieve control of speed in induction motor. Now all these speed control measures are also classified on the basis whether the control is achieved from stator side or from rotor side. Now the change of frequency in stator winding, or change of number of pole in stator winding, or supply of variable voltage to stator winding is called stator side control of speed in an induction motor. And these stator side control can be used in both squirrel cage induction motor as well as in slip ring type of induction motor. But the other method, that is extra resistance in rotor circuit, or injection of slip frequency EMF in rotor circuit, or cascade operation of two slip ring induction motor, are speed control measure of rotor side, and such rotor side speed control can only be used for slip ring type of induction motor which have a phase wound rotor, and there exists a provision to add either extra resistance or external EMF in rotor circuit, and that can be used to change slip and speed of induction motor. So such control known as rotor side speed control are discussed in another video of the same playlist, and today we will discuss stator side speed control of induction motor in great detail. The most convenient, simple and economic speed control of induction motor from stator side is stator voltage control. Now the speed control of induction motor can be achieved by controlling stator terminal voltage, but practically we cannot increase voltage beyond the rated voltage of induction motor, as increased voltage will increase insulation stresses on stator winding, and that may lead to insulation failure. So we can only reduce stator applied voltage. Earlier this reduction was done by adding either series resistance or reactor to motor circuit. When we add resistance, it increase operating losses, and when we add reactor, that reduce operating power factor. So both have technical problem. So now in modern stator voltage control, we use electronic AC voltage controller based on thyristor family devices, and those SCR based AC voltage regulator economically, efficiently can control stator applied voltage as per our requirement. Torque and slip relationship of an induction motor is shown in this blue frame, and relation indicate that torque apart from slip depends upon stator applied voltage, and torque is directly proportional to square of applied voltage, and it also depends upon per phase rotor resistance R2 and standstill rotor per phase leakage reactance X2. In normal running condition from no load to full load, the slip of motor is so small that at slip frequency rotor leakage reactance Sx2 is small compared to per phase rotor resistance R2. So we can neglect square of Sx2 in comparison to R2 square, and when that black highlighted Sx2 is neglected, we can simplify torque and slip relation. We can say torque become directly proportional to product of slip and square of applied stator voltage. It means if we reduce applied voltage, the same amount of load load torque will occur at higher value of slip, and motor rotating speed is related to synchronous speed with slip as given by this yellow highlight relation, and higher the amount of slip when you have reduced applied voltage, lower would be the operating speed. Now during this voltage change, we won't have to change frequency of electric supply given to stator, only the voltage magnitude has to be reduced. Torque and speed relationship of an induction motor for three different voltage V1, V2, V3 are shown here by red, green and blue characteristic, and these characteristic indicates that slip of maximum torque or speed of maximum torque remains the same irrespective of change in applied terminal voltage to stator winding, and we know slip of maximum torque called as S maximum approximately depends upon per phase rotor winding resistance and standstill per phase rotor leakage reactance. As these two parameters are constant, when you change applied terminal voltage, SM will not change, and the stable operating region of torque and speed shifted when you reduce voltage from red to green, or further reduction of applied voltage will shift that characteristic to blue characteristic region, and to obtain same amount of torque we can reduce speed. For an induction motor of fixed per phase rotor resistance and fixed per phase rotor leakage reactance, the starting condition slip is 1 and constant, so torque is proportional to applied voltage square, and similarly the slip of maximum torque is also fixed SM, so for fixed value of SM again torque is proportional to V square. So we can say that for a particular value of slip, torque is proportional to applied voltage square, and when you reduce voltage from V1 to V2 or further reduce V3, the torque of any speed or any slip will proportionally reduce as square of voltage, as shown by these three red, green and blue characteristic of three different voltage. V1 is greater having red characteristic, V2 is mid voltage having green characteristic, and V3 is lowest voltage having blue characteristic. So for same amount of torque, when applied voltage is reduced, to obtain the same amount of torque, operating slip increases and motor rotation speed decreases. But normally in fan and pump type of load, the load torque is proportional to square of speed. So when speed of motor is reduced, simultaneously load torque is also reduced, and motor operating point at highest voltage V1, which is at C position, shift to B or A position when voltage is reduced to either V2 or V3 level, and smooth reduction of voltage can take appropriate lower slip operating position, and we can control speed by change of applied stator voltage. And this application of speed reduction is quite suitable for fan type of applications where torque demand reduces as speed reduces, and in fan and pump torque is proportional to square of speed, and reduction of maximum torque capabilities with reduced voltage won't create trouble in obtaining required load torque at reduced speed. This stator voltage method of speed control of induction motor is the easiest and the cheapest. It is very simple, convenient and economic, but still it is rarely used. And the two good reason for that is, the first reason is, in this stable region of operation, torque is proportional to product of slip and voltage square. So to make small amount of change in operating speed by slip, we have to make large amount of change in applied voltage, and large voltage change results in very small change in speed, and the maximum amount of change which we can produce is up to speed of maximum torque. Beyond that we cannot make change in speed, and for economic design of induction motors, the slip of maximum torque is only 5 to 8%. So by change of voltage, if full load slip or slip of maximum torque is small, we can't make good amount of change in speed by this applied voltage control. Now when we reduce applied voltage, the working flux density between stator and rotor in the air gap also get reduced, and that reduce the maximum torque capabilities of motor. Hence reduced speed operation also reduce maximum torque capabilities of motor as we reduce applied voltage. A popular and convenient method of speed control by stator voltage control is used in domestic ceiling fans, where we change applied voltage to stator of ceiling fan by using a diac and triac pair, and the fixed voltage AC supply is controlled by diac and triac pair, and diac control triggering angle of triac, and when we control delay angle of conduction of triac, and triac is triggered with alpha delay angle in both positive and negative half cycle, the conduction period get reduced and effective RMS applied voltage to stator get reduced. The squirrel cage rotor of domestic ceiling fan is designed with high value of per phase rotor resistance that results in higher value of slip for maximum torque condition, and it also results in a larger range of stable operating region where torque and speed got negative slope characteristic, and increased speed results in decrease of torque. So at rated voltage operation, ceiling fan operate at rated speed conditions, but when we reduce voltage, the torque reduces proportional to square of voltage, and at the same time reduced speed also require less amount of torque for blade rotation, as for fan torque is proportional to square of speed. So torque requirement by fan blade and torque produced by fan motor both reduces to a new operating condition which is having smaller amount of speed, and similarly further reduction in voltage from V2 to V3 or V4 or V5 results in reduction in required load torque as well as reduction in operating speed, and we can have a considerable reduction in operating speed of ceiling fan by reduction in applied voltage. But the fan, when designed with higher amount of rotor resistance and operate at higher amount of slip, it would have higher amount of rotor copper losses, and reduced speed operation become relatively energy inefficient. When the stator of induction motor is designed in a special manner and its winding can change its pole number, then we can use pole changing method of speed control for squirrel cage type of induction motor. The rotating magnetic field got a synchronous speed, and that synchronous speed is given by relation 120 F over P, where F is supply frequency and P is a number of pole in stator winding. And if we use a squirrel cage rotor, then this method of pole changing can change synchronous speed of rotating magnetic field, as rotating magnetic field synchronous speed is inversely proportional to number of poles. When pole number is increased, the synchronous speed get a stepped reduction, and for the same amount of slip to produce same amount of torque, we can have reduced operating speed of squirrel cage induction motor. One important thing is the rotor of slip ring induction motor got a fixed number of pole, and for rotating operation in three-phase induction motors, the number of pole in stator and rotor should be the same. So this pole changing method cannot be used in phase wound slip ring type of induction motor, whereas in squirrel cage induction motor, short circuited metallic cage winding of rotor can adopt itself for any number of poles. So when stator pole are changed by special reconnection of winding coils, the rotor itself adjusts for number of poles in rotor winding identical to number of pole in stator winding. So this method of pole changing method can be used only for squirrel cage induction motor, and when stator pole number is changed, that change synchronous speed of rotating magnetic field, and that results in stepped change in operating speed. For pole changing method of speed control in squirrel cage induction motor, change in stator number of pole is achieved by two or more independent stator windings wound for different number of poles in the same slots of stator. As in this high number of pole configuration, the coils are delta connected, and three-phase line connection is given to one terminal of phase U, V and W, and this winding works as a higher number of pole and motor rotates at low speed conditions with this configuration. And when one U, one V and one W are interconnected to form a star, and these two U, 2V and 2W are given three-phase line, this winding become a double star winding with less number of poles, and now this winding operate at high speed. So by just changing winding coil connections in this special designed winding, we can change number of poles, and when pole number is increased, the operating speed get reduced. But such special design of stator winding is very difficult, and this can be made only during manufacturing by special design features, and that also increase cost of induction motor. And since stator is compromised for this special design, the operating efficiency and performance of such motor is also inferior compared to standard single pole winding. So normally this method of pole changing for speed control of induction motor is rarely used nowadays, as we have a far better method of speed control by variable frequency supply, which smoothly, gradually and continuously control operating speed of induction motor, whereas in this pole changing method, speed control can be achieved only in steps, not in a continuous regular fashion, and machine for such special pole changing provision become costlier and have relatively inferior operating characteristic in comparison to standard single pole squirrel cage induction motors. Such special designed motor having two set of winding in same slots of stator are called pole changing motor or multi-speed motors. Now while in operation, we can select low speed connection of three-phase supply or high speed double star connection of supply according to the speed requirement of user, but the change of one speed connection to another speed requirement connections require considerable effort and a time gap. So the control of speed by pole changing method is not convenient, and secondly, speed change is also not gradual and continuous. It is only stepped change in speed. We can explain speed control by pole changing method by this example. For example, for Indian supply frequency of 50 Hz, a three-phase squirrel cage induction motor stator winding is wound for 2 number of pole, one for 4 number of pole and other for 6 number of pole. So with 4 pole winding with 50 Hz supply frequency, the synchronous speed of rotating magnetic field is 1500 rpm, and with this synchronous speed, the rotor of induction motor at no load with 0.5% slip rotate at nearly 1492 rpm, and in full load condition when slip become 5%, the rotor speed got a small speed regulation of 4 or 5% of synchronous speed, and if all of a sudden we change number of pole from 4 pole to 6 pole, the synchronous speed of rotating magnetic field will change from 1500 to 1000 rpm in a step, and as synchronous speed changed to produce same amount of torque with the same amount of slip, as synchronous speed of rotating magnetic field has changed due to change in number of pole from 1500 to 1000, the operating speed at full load conditions shift from 1425 rpm to roughly 950 rpm. So we can change speed of operation of induction motor in a step to two different required values, and if process require two different operating speed conditions for a certain performance, then the same motor designed for two number of pole can be used to perform its duties for two different speeds. But look, special design and manufacturing of stator for such a pole changing arrangement is very expensive, as it involves multiple stator winding in same slots, so higher amount of copper, and in comparison to a standard single pole designed motor, the running performance of this motor is inferior in terms of efficiency, torque production and operating power factor. The speed control of induction motor by pole changing method is possible only in squirrel cage induction motor, whereas this modern variable frequency supplied to induction motor can control speed of both squirrel cage and slip ring type of induction motors, and for that we have to use a variable voltage variable frequency special three-phase supply for stator of our induction motor, and this special variable voltage variable frequency supply is also known as VVVF supply, variable voltage variable frequency supply. And we know the synchronous rotating speed of magnetic field in the air gap is directly proportional to supply frequency, and when supply frequency is changed, we can change rotating speed of air gap magnetic field, and rotor of induction motor with a certain amount of slip as per the torque requirement of motor will have changed speed of operation if supply frequency is changed. Earlier, when power electronic devices were not available and supply frequency is very difficult to change, we can use only stator voltage method of speed control, or we have to design stator for special two different pole configurations, or otherwise we have to use slip ring type of induction motor. But nowadays we can change frequency of supply easily by modern power electronic devices of thyristor family, and such systems of variable frequency supplies are called as inverters, where the fixed three-phase supply of fixed voltage and fixed frequency is first converted into DC, and this DC power is converted into AC of variable voltage and variable frequency by modern power electronic inverters. And this variable voltage variable frequency supply, when given to stator of induction motor, we can control speed torque characteristic in such a way that operating speed of motor can be controlled to the both higher side of rated speed as well as to lower side of rated speed. When a rated frequency supply at rated voltage is given to stator, the synchronous speed of rotating magnetic field is at rated condition, and with certain amount of slip, motor operate at rated speed. Now, to reduce speed from rated speed, we can reduce supply frequency, and when supply frequency is reduced, we also reduce applied voltage to stator so as to maintain constant voltage to frequency ratio. And when voltage to frequency ratio of supply applied to stator is maintained constant, then the magnitude of flux in air gap between stator and rotor also remain at constant value, and as per rotor current capacity and constant flux operation, motor have a constant maximum torque production capacity, but reduce synchronous speed of rotating magnetic field, and for the same amount of slip to maintain constant torque, the motor operating speed will reduce as we reduce frequency and voltage in the same proportion, and reduced frequency maintain constant torque conditions of load at different reduced speed operations. So this reduced frequency operation with constant V and F ratio, voltage to frequency ratio, is also known as constant torque region of speed control. Whereas to increase speed from base speed, we have to increase supply frequency, and when we increase supply frequency, synchronous speed of rotating magnetic field increases, but we cannot increase supply voltage beyond rated voltage because increased voltage will increase voltage stresses. So to maintain insulation of winding safe, we operate motor at high frequency with constant voltage, and in that condition the magnitude of working flux get reduced, and due to field flux reduction, the maximum torque capability of induction motor also reduces. And if our torque have a reduction in magnitude with increased speed, if it is a machining tool operation like lathe, turning or shearing type, where increased speed require lesser amount of torque, then this method is very convenient, and with reduction in load torque at increased speed, we can have different operating conditions with increase of frequency. And this operation where increased speed reduce motoring torque is also known as constant power region of speed control. So an induction motor have both reduction of speed from base speed or increased speed operation from base speed by reduction of frequency or increase of frequency. But when we reduce frequency, we maintain constant flux by constant voltage to frequency ratio. And for increased speed operation, when we increase frequency, we can't increase voltage, and voltage is kept at rated value, and in this operation field flux get reduced, so the torque capability of motor get reduced. So if a torque got constant power characteristic at different increased speed, then this increased frequency process can be used to increase speed of induction motor. In another video of the same playlist, this variable frequency speed control is explained in great detail, and the link for the same is given in description as well as in end screen conditions. We hope this learning video has explained all stator side speed control method of three-phase induction motor, and now you understand the working of stator voltage control, special pole changing methods, or the most versatile variable frequency supply to stator. In another video of the same playlist, we have discussed rotor side methods of speed control of three-phase induction motor, and in another video we have discussed variable frequency drives in a good detail. Our other learning video of the same playlist will enhance your learning about induction motor, and other playlist will improve learning of other subjects. If you found these learning work useful, do share it with your friends. Happy learning. Thank you very much.